Thank you so much. I think this was the warmest and most heartily and competent and comprehensive introduction that I've ever experienced in my life. Thank you very much, VODA. It's a great pleasure, and I would like to start with the thank you here. It's a great pleasure to be here. Thank you for the invitation and the really, really nice venue and organization. Everyone also in the background. Thank you very much. Then, content-wise, my big thank you go to Viviane and Heinz. Heinz and I co-supervised Viviane for her PhD, and I decided today to not give you a superficial talk about combined sewer overflows and micropollutants, but to dive a little bit into specific technical aspects and hopefully data, take you on a journey, data that you probably have never seen like this before. Then I would like also to acknowledge my co-authors or the co-authors of Viviane in the 3 papers that she published. I think all this is open access, and I reference it in the presentation, and so you can read all the details if you want in these as well. Then obviously we always need a lot of support for this PhD thesis, so there is technicians and master students, and I'm very happy and give on and pass on the credits to them as well here. And obviously, last but not least, it's almost not visible. Thank you to the Federal Office for the Environment for having funded this PhD. VODA already said the title, is there a solution, an easy solution for micropollutants in combined sewer overflows? And I can take it away. This is the smart answer of the scientist. No or yes, or it depends. And I would like to show you both that there is conceptually a yes and practically a little bit more challenging, rather a no. You all know that micropollutants occur in rivers. Many have measured them before. This is a comprehensive review by Fink et al. In 2024. They measured a couple of rivers, or they compiled data from a couple of rivers, and they see that many, up to dozens to hundreds of micropollutants can be measured, and they also exceed temporarily ecotoxicological thresholds. Where do these micropollutants occur from? You are all experts, you know this as well. There are plenty sources in the urban areas. Many hundreds of thousands are registered synthetic chemicals, and certainly over 30,000 are in daily use. They have these different sources that we use in everyday life, detergents, pharmaceuticals, but then also biocides and plant protection, but also most recently we were made aware of tire wear, leachates, tire wear particles, and what leaches from them. Typically during dry weather, in both the separate and the combined sewer system, they go into the wastewater treatment plant. Wastewater treatment plants are well studied. We know what the removal is. We increase the removal with additional treatment steps. But then when it rains, some of it cannot be handled by the wastewater treatment plant, and it is discharged mainly untreated or with minimal treated, particularly the dissolved phase is not treated. And there are many sites. Do you know how many sites are in Switzerland, combined sewer overflows and separate stormwater inlets? Or in Europe? In Europe it's over 500,000, and in Switzerland it's also 50,000 or more. So there is many sites, and it's difficult to monitor them. And we also anticipate that combined sewer overflows, the events will increase in the future due to the climate change with more frequent and more intense rainfall. Lena and Viviane, they compiled on this graph, and I'm sure you cannot read it from the back, but that's also not necessary. They have compiled in the few studies for micropollutants and CSOs how frequently they were detected, so from 0 to 100. And it's evident that almost all the substances were almost always detected. On the other axis here, we have the risk quotient. So this is the measured concentration divided by the environmental quality standard. And as soon as this exceeds 1, there is, like, it exceeded the environmental quality standard. And so it's important to see that many substances are in this top right corner where concentrations exceed the environmental quality standards, and they are detected in each event. What the big problem is, and what we didn't know until now, is all these studies are based on event mean concentrations. We don't know what the dynamics is because it's very time-consuming and difficult to get all these samples, so we have very little idea of what the temporal evolvement of concentrations in sewer overflows are, in combined sewer overflows are, and so they are really often only based on these event mean concentrations, and this is the research gap. Very little is known at high temporal dynamics, and from this, Viviane concluded the 3 research questions for her PhD. What sampling interval is required to properly assess the dynamics of the concentrations in combined sewer overflows? If this was the true one, is it sufficient to take every 10 minutes, every half an hour, or is it needed to be more? And then what do we observe as source-specific dynamics? Do we see different dynamics depending on what the source is of these? For example, from the households, what I refer to often as indoor substances, or then outdoor substances, what originates from plant protection or from the road. And also ideally to see, is this different from one event to the other, or is it always relatively similar? And then the third research question was, what does this dynamics imply related to aquatic risk, related to the risk that aquatic organisms are exposed to? And the main question there was, what is the maximum compared to the event mean concentration or the mean risk quotient, and at what time does it occur, which would help us to give practice advice on how to best mitigate the risk in combined sewer overflows. Viviane conducted 2 measurement campaigns, one in a small catchment with roughly 3,000 people and 17 hectares reduced, to give you an idea about the size, mostly household, roads and agriculture. She conducted this in 21-22 and monitored 16 events and collected over 300 samples at the temporal resolution of 3 and 10 minutes, and I'll show you the data in a second. The second catchment is a rather large catchment with almost 160,000 people, 368 hectares reduced, and in addition has a little bit of industry. Also there, she monitored almost for a year, overall 8 events with a total of 240 samples analyzed, also at the temporal resolution of 3 and 10 minutes. The substances she analyzed with LCHRMS, it is a sum of 64 dissolved organic micropollutants, which originate half from indoor substances and the other half roughly from outdoor substances. It is mostly pharmaceuticals for the indoor compounds, and then plant protection products, biocides, some as pesticides, then some that are not in use anymore, some that are originating from the road, and some that have multiple sources. So what is the required sampling interval? How much do organic micropollutant concentrations fluctuate during CSO events, and what are the influencing factors? Let me briefly explain this. On the left, you see the data for 2 substances, for paracetamol and metoprolol, for the small catchment over a time span of about an hour and 10 minutes. And on the right side, you see the large catchment, the data from the large catchment, also about an hour of duration. And what becomes apparent, this is at the 3-minute temporal resolution. She took grab samples every 3 minutes, and what you see here is like this could be an individual toilet flush. It only lasts about 6 to 10 minutes, and it can go from almost 0 to up to 20,000 nanograms per liter. Also down here for metoprolol, you see similar development with individual peaks here. It is a little bit less pronounced, but can still be a factor of 2 within 6 minutes, also in the large catchment for both of these substances. What does it look like for outdoor substances? Here we have the 1,3-diphenylguanidine, which is originating from tire leachate, from tire wear particles, and mecoprop, a pesticide. And what you see is that there is not so much variation. I was really surprised to see that there is not much more variation in both the large and the small catchment. So the variation is much smaller than this here on a relative scale. To be sure that the 3-minute grab samples are not just coincidence, we also measured 10-minute composite samples. She took every 2 minutes a sample, made a composite sample in a 10-minute, which we assumed this will cover everything. And as you see, the blue and the red, the composite and the grab samples, they agree quite well. So concluding from this, as an intermediate conclusion, we have variation that depends on the size of the catchment. In the smaller catchment, it can be substantially larger than in the bigger catchment. The indoor substances, they vary substantially more than the outdoor substances, and that if you want to know this correctly, you have to take samples at the high sampling frequency, at the very short interval. This is, as I said, the reference where you could read more details. Now we were interested if we have source-specific dynamics that we can observe. The specific two research questions in this context were if we can observe specific dynamics in the from the different sources in the combined sewer overflows, and in a second step also if for all the non-targets, I forgot to mention this, besides the 64 target substances, HRMS, high-resolution mass spectrometry, allows you also to analyze hundreds to thousands of non-targets where you can identify the intensity and see whether or not these match with the time series that we measured for the target substances. So first we took the target sample, the target substances, and measured how much or how similar are the different time series to each other. Here for the indoor substances, and you see again the small catchment on the left side and the large catchment on the right side. And what we can see is that on the different indoor substances among themselves, they show high correlation. So they show all similar patterns, but only in the large catchment. In the small catchment, different peaks occur at different times, and it's not easy to derive a common pattern. We've also done this for the other sources, for the road substances and for the pesticides. And what you see is that, as you can have anticipated from the time series before that I showed you, that in both catchments, in the small and in the large catchments, these road substances, they show very similar behavior, so they correlate nicely with each other. But the pesticides also in the large catchment, they occur at any time and there is no correlation among different pesticides. Because micropollutants are very time-consuming and expensive to analyze for, we wanted to know if the target time series of micropollutants also correlate with other parameters, for example, flow or dissolved organic carbon or ammonia, which would be easier to measure as proxies. And this is what you see here. Unfortunately, only for the indoor substances in the large catchment, we saw some correlation, negative correlation with flow. Basically, the precipitation dilutes the indoor substances, and it correlates positively with dissolved organic carbon and with ammonium. And for the rest, for all these other, they did not correlate. We don't see any correlation, which makes it very challenging to generalize what mitigation options are. So source-specific dynamics can only be found for the large catchment for indoor substances and road substances in both catchments. And in the large catchment, one could estimate or assess the concentrations of other micropollutants based on the dilution that we measure or that could be measured. Now to these non-target time series. The time series that we measured from the roughly 30 indoor substances are the ones in brown here, but then over 3,500, almost 3,500 substances, they show the similar pattern as these that we anticipate that would also originate from indoor sources. And the same holds true for the road substances, where we only measured 3 substances, but 150 other non-target substances that HRMS revealed showed very similar, where we anticipate that they also originate from the road. Overall, this leads us to the intermediate conclusions that the actual target lists that we typically analyze strongly underestimate the existing pollution, and that many substances with a large depot on urban surfaces must be there, as we saw for these road compounds, but we would have anticipated that we'll just go with the first flush and then they will not occur anymore, but this is not the case. And that raw wastewater is an important pollutant source, as we have seen with the many additional substances here, non-targets that show similar pattern. This can be read in more detail if you're interested in this publication. Then related to the chemical risk assessment, which is what we made the study mainly for, is what are the outcomes of the chemical risk assessment at high temporal resolution, because until now this was only possible with event mean concentrations and for the chronic environmental quality standard. And so what we did is we took the individual measured concentrations and we calculated the total risk, and we've done this. I just showed two examples here. Take the acute quality criteria for the individual substance, and then we divide the concentration by this acute quality criteria, and we sum them up, which is a commonly accepted methodology in environmental risk assessment. And what you can see here is a very complex graph, and I'll explain it to you in detail. This is the time course of how this risk evolves over time. It's about a 2-hour event here. We have the different substances in different colors, coded according to the legend up here. There is the inflow into the combined sewer overflow here, depicted with the black line. Then the risk quotient of 1 that we would want to not exceed is labeled here is the red dashed line. The event mean concentration, or the mean risk quotient, is labeled here in the green dashed line. This is what we would have achieved with mean concentrations. And what you now see here is these 10-minute composite samples and the risk quotient that we calculated for these individual 10-minute intervals. And what you see here is that they exceed substantially the level of 1 over time here. What you also see is that there is many different compounds that are responsible for this exceedance. Here it's mainly this red one, which is clindamycin, which is an antibiotic, but then later in the event you see that there is mainly 2 substances, pesticides, that are responsible for this. And as you can imagine, this is very challenging. We often talk about the first flush, which may be correct for indoor substances if we try to assess the, or reduce pollution from sewer overflows for the first flush or for particulate matter, but you see that also later in the event there is substantial exceedance of these of the aquatic thresholds, of the environmental thresholds. So it's a very diverse dynamic, and there is no general window with higher or lower risk. So I only showed you one, but Viviane analyzed many events, and we could unfortunately not conclude any generalizable results, which part of an event would be best to be retained, and that only partial retention or only partial treatment is not sufficient to reduce the overall risk. Luckily, only about 20 substances were the ones driving these main risk, and you see here overall events that we analyzed, again, these substances and how they exceeded the risk quotient of 1. We labeled here the different substances according to their origins. So the Swiss Water Protection Ordinance is the ones labeled in blue. Typically observed in combined sewer overflows are the ones in purple, and the orange one is a more comprehensive list, and so you see that you need different sources or different lists to be combined to cover all the most critical substances. So only a few substances drive this overall risk from what we see now, because we also have not so many acute aquatic quality standards. It is pharmaceuticals, pesticides, and roads that are important sources, and in Switzerland only a part is covered of these 20 substances, which makes us rethink how we could revise this list or add substances to this list. And you could see this also in this publication that Viviane wrote. So concluding, related to the sampling interval, short-term fluctuation depend on the catchment size and source, and as you know, many of these catchments are rather small where we have combined sewer overflows, and a high sampling interval is required. The 3 minutes does not mean that you have to analyze all the samples individually at 3 minutes, but you have to take the samples at 3 minutes and you could pool them, and then you would have a reliable composite samples, maybe 10 minutes for these short-term fluctuations, or maybe reliable event mean concentrations. Related to the second point, generalizable dynamics for indoor substances could be derived, at least for the large catchment. In the small catchment, that's occurring more or less a little bit at random times. And for the road substances from surface runoff in both catchments. We've also seen that many non-target compounds, especially from indoor sources, would complement the picture, and so we make efforts to further dig into this, and that there is a strong dynamics of the total risk, and that all sources, indoor, roads, and pesticides contribute substantially to this risk. What does it mean, or what does it imply for practice? It means that we should choose sufficiently short sampling intervals, and that proxies only can partly help to analyze or reveal source-specific dynamics, or serve as proxies instead of analyzing the micropollutants themselves individually. And for the design and the mitigation, it is important to see that the large number of substances implies strong dynamics and many relevant sources at many sites, which is challenging for mitigation measures. Most importantly, the first flush reduction is not sufficient, so bottom line or recommendation here is that every cubic meter that we can retain in the system helps, and this does not only mean retaining in concrete substances in combined sewer overflows, but maybe also think about blue-green infrastructure and retain it so that the flow into the sewer system is slower. And then obviously what is less in our hands is the regulation at the source or a ban of individual substances. And then an outlook for you and for us. We have to identify parameters to explain the dynamics better. I'm a bit reluctant. I doubt that we will succeed in this. It seems that each catchment and each combined sewer overflow and each event can be different, and we don't know what to anticipate exactly. And related to the risk is a call for environmental toxicologists, so that we need more data on acute quality criteria, particularly for short-term exposure and effect assessment. And that in the stormwater, that the risk from tire wear, leachates, and the impact of infiltration on groundwater quality needs to be studied, because if we retain it in the system, or if it, with blue-green infrastructure, goes into the ground instead of into the sewers, this needs to be investigated in more detail. And then, as a last one, safe by design chemicals. And with this, I would like to thank again all my colleagues who contributed to this work, and you for your attention.